My screen sharing, is it visible? Am I audible properly?
Yes, sir. Clear.
Okay. So in our last session, we were discussing about combinational circuit. So the last topic that was left was what? It was your decoder. So what do we mean by decoder? So a decoder is a circuit which basically converts a n-bit binary code to M output line. Okay, n-bit binary code to M output line, or simply you can even say that it is your binary to decimal converter. Okay, binary to decimal converter. So basically, input, we have n bit input and we have M output line. So we basically give what? We give a combination of input in binary string. According to that, only one output line is activated, that is known as your decoder. Now decoder, it can be of various sizes. It can be 2 cross 4, 3 cross 8 decoder. So one of them is your 3 cross 8 decoder. So in 3 cross 8 decoder, basically we have three input lines. Okay, three input lines, and we have 8 output lines. So using a string of input, a string of binary input, we activate any one of the line. Okay, any one of the line, and this is your enable input. Enable is like kind of a switch. Okay, if enable is 1, so this is enable high. If enable is 1, then only this decoder, this 3 cross 8 decoder, it will be operational. If this enable is 0, whatever input we give, decoder, it will always have 0 output. It will not produce any output. So basically, this combination of A, B, C can be see. Whenever our input is 0, 0, 0, means like this, we will have D2, D3, D4, D5, D6, D7. Instead of writing all this, what we can do, simply we can write the corresponding minterm that will be activated. So whenever A, B, C is equal to 0, so D naught will be activated, and corresponding minterm to this, it will be what? It will be A complement, B complement, C complement. Whenever A, B, C, so here A is MSB, C is LSB. I have assumed it like this way. So whenever A, B, C, A equal to 0, B equal to 0, C equal to 1, D1 line will be selected, and the corresponding minterm to this will be what? A complement, B complement, C. Similarly for this one, it will be A complement, B, C complement. This will be A complement, B, C, A, B complement, C complement. This will be A, B complement, C. This will be A, B, C complement, and the last one will be A, B, C. Okay. So here you can see what? That basically we are making min terms over here. Out of any one of the 8 output lines, only one is being selected, and we are passing them this min term through this output. Okay. Now suppose if I want to pass max terms over here, so these are all your sum terms. Okay, sum terms you can see. Sorry, these are your product terms. Suppose if I want to pass sum terms over here or max terms, so what are we going to do? Simply, the circuit is going to look the same way. Only change will be this, that your output will be bubbled. So there will be a bubble. So due to this bubble, what will happen? So bubble corresponds to your complement. Okay, it corresponds to your complement. So simply, when we pass through D naught, this was the minterm we were getting, and there will be a whole complement above this. So this will be what? A plus B plus C. And we also know that when we want to write your sum terms or max term, 0 corresponds to normal variable and 1 corresponds to complemented variable. And this we can see over here also. If I wanted to write max term corresponding to A equal to 0, B equal to 0, C equal to 0, it will look like this. Or if we simply take the complement, it will be A plus B plus C, which we are also getting. Again, if we take complement, so this will be what? This will be A plus B plus C complement. If we take complement over here, so this will be A plus B complement plus C. So this will be A plus B complement plus C complement. This will be A complement plus B plus C. This will be A complement plus B plus C complement, and this will be A complement plus B complement plus C, and this will be what? A complement plus B complement plus C complement. So what are we getting? Basically, we are getting our answer in terms of your max term or your sum terms. Okay, is this clear? Any doubt?
Clear, sir, clear.
Okay, fine. So now we have a question. So a very simple question, this one. So you can see basically it is used to generate max term or min terms. Okay.
So it's bubbled, and
Yes, it's
output is
bubbled.
bubbled.
Yes,
So it's a max
outputs are
term.
bubbled. So obviously you can see if output are bubbled, that means you will be getting max term. And max terms, if you pass it through your AND gate, you will be getting POS. Okay, POS you will be getting. So you need to check which of the option is correct.
And 1, 2, 4, 4, 7.
So 1, this will be what? Max terms will be 1, 2, 4, 7. So this will be what? It is denoted by function is equal to pi capital M 1, 2, 4, 7. Suppose, suppose if this option was not given, instead of this it was given, okay, this option was given. Suppose this option was not present and even this option was present. Then what will we do? Okay, so you can see even option A is given. Option A is given. So will we mark this? So I didn't see, means this option was also given. I have only told you that if all the terms which are min terms over here, okay, the remaining terms will be max term if nothing is said about your what? If nothing is said about don't care. So there is no mentioning of don't care. So what do you think? Can I mark option A also correct? Or only option C is correct?
So just tell me once more what you have just said right now. Like
I
don't
told
care.
means in a Boolean expression or in a K map, okay? In a K map, I have already told you. Suppose one is filled in all those positions. Okay, one is filled in all those positions. So what do we mean by the vacant position? This position, this and this. If nothing is said, if don't cares are not mentioned, what we know that these are going to be your zeros These are going to be your zeros. So that is what I am saying. In this function, you can see that this corresponds to what? This corresponds to your POS. So the remaining cells that are your 0, 3, 5, 6, they might be filled with 1. Can I assume so? Can I assume so?
Nothing is mentioned.
Yes, nothing is mentioned, but I cannot take it over here. Why? Because you can see these are your floating points. Okay,
Right, right.
these are your floating points. So I cannot mark option A. I will be just marking what? Option C as my correct. Okay, so option C will be correct. Okay, so Surjit is waiting in the lobby. Okay, so now let us start with. So this chapter is over. I will ask all of you to go and solve the question of all the gate questions. Also, I will suggest you to solve for combinational circuit. It's okay. Means why I am asking all of you to solve gate questions also. Gate questions, I know each and every question on an average it takes 3 minutes. Okay. On an average it takes 3 minutes. But sometimes what happen, they will ask, means this HAL exam, in HAL exam, they might ask you one question which won't be taking you like 3 to 4 minutes, but it will take 1 minute, and that concept will be based on some of the questions of the gate. Okay, some of the questions. So basically they will just ask you some part of a question. Okay, so due to that I am asking you to solve gate questions and all the ESE engineering services prelim paper. Okay, prelims paper. That's it. Nothing else is going to be asked out of this. Okay.
Okay.
Okay, so one more topic that was left is your parallel binary adder, but I don't think this will be asked, because if these questions are asked from parallel binary adder, so those questions will be either it will be of your this propagation delay. Okay, and those question it will consume lot of time. So here I have just given a very brief, very means small explanation for what is a parallel binary adder. Okay, so suppose if I want to add two or more 1-bit number, like A is equal to A1, A naught, or B is equal to B1, B naught, or even if I want to add 4-bit number, A3, A2, A1, A naught, or B3, B2, B1, B naught. So this is two 2-bit number, and this is also two 4-bit number. Suppose if I want to add this. So what is a group of 4 binary bit known as? Group of 4 binary bit?
Nibble.
Pardon?
It's nibble something.
Yes, it is known as nibble. Okay, group of 4 binary bit, it is known as nibble. So sometimes what happens, we want to add such kind of numbers, so we take help of parallel binary adder. In this also I have just taken ripple carry adder. I haven't taken your look ahead carry adder, due to the fact that look ahead carry adder it is not going to be asked over here. So now in this ripple carry adder, what happens, suppose if we have a 4-bit number. So I will just make you understand with an example. Suppose A is equal to 1101 and B is equal to 0101. So at T equal to, so it is also written a group of 4-bit is called nibble. So I have written over here. So at T equal to 0, why this is known as your binary parallel adder, you can see at T equal to 0, what happens that all the bits are going to be applied simultaneously. Okay, so here you can see A naught, B naught is 1 1, A naught, B naught is 0 0, sorry, A1, B1 is 0 0, means A is having this structure. Okay, so you can see B1 is 0 0, B2 and A1. A2 is both 1 1, and B3 and A3 is 1 0. So this is applied at t equal to 0. All the inputs are parallelly applied to your full adders. Okay, so a ripple carry adder is constructed using full adders. So you can say if there is 4 bits, so we are going to require 4 full adders. If there are 2 bits, we are going to require 2 full adders. So if you see over here, I have applied all the inputs initially. Now what happens? Look at this state. So any full adder has 3 input. Full adder has 3 input, 2 bits. Okay, the 2 bits are what? Input bits, and 1 carry input. So over here, initially Cin is equal to 0. Okay, Cin is 0. So at t equal to 0, basically I have all the 3 inputs of this adder. Now if I assume this to be an ideal ripple carry adder, what do we mean by ideal? That none of the full adder have delay. Okay, none of the full adder have delay. Then what will happen? Basically, immediately you can see what? That all these bits will be added immediately. Means what? Immediately you will be getting a plus b equal to 1 1. So sum will be 0, carry will be 1. So at t equal to 0, as there is no propagation delay anywhere, so immediately this will be 1. So the moment you can see Cin is 1, a1 0, b1 0. So and Cin 1, so this will be 1, carry out will be 0. So again you can see here sum to s2 will be 0, carry will be 1. And once again here you can see sum will be 0, C out will be 1, and we know what? This will be 0 1 0 1, sorry, 0, and carry out will be 1. That is what we are getting. Okay, so this is the ideal case when all the carry we are getting at t equal to 0 due to the fact that all the full adders have no propagation delay. But what happens in full adder? We have propagation delays. Okay, propagation delays. So let me talk about that. So in full adder, we have two kinds of propagation delay. Some propagation delay and carry propagation delay. Now, what do we mean by this some propagation delay and carry propagation delay? Can you tell me? Anyone? Can anyone tell me what is some propagation delay and what is carry propagation delay? Look at the name. Okay, some propagation delay means how much time all the full adders. So these are what? These are identical full adders. Okay, identical. So some propagation delay means the delay that all the full adders are taking to generate the sum terms. Okay, sum terms. And carry propagation delay means what? Carry propagation delay means the delay that all the identical full adders take to produce this carry. Okay, this is known as what? Carry propagation delay. Now in our example, let us take some propagation delay as 1 microsecond and carry propagation delay as 2 microsecond, and let us see when do we get the final output. So what is the final output over here? So final output will be S3, S2, S1, S0 along with this C out. Okay, C out. So let me write it as this is C out 0, C out, this is C out 0, C out 1, C out 2, C out 3. Okay, along with C out 3. So this is your complete output. So let us see when do we get this output, after what time instant. So listen very carefully. This might be asked in your HL. So look, at t equal to 0, we apply all the inputs. Okay, we apply all the inputs, but now this time we have finite propagation delay. Okay, 1 microsecond is some propagation delay and 2 microsecond is carry propagation delay. Tell me, up to this point, is everything clear to both of you, Shriyari and Surjit? Is it clear?
Yes, sir.
Okay, okay. So now look, okay, now look. You can see at t equal to 0, all the inputs are applied. And this Cout, it will be produced after 2 microsecond, whereas this sum, it will be produced at t equal to 1 microsecond. So after 2 microsecond, what will I get? That these two bits are 1 1. So Cout will be, means S0 will be 0. Okay, S0 will be 0 because these two bits are being added. 1 plus 1 is 0. Carry out will be 1. And this we are applying at t equal to 2 microsecond. So this full adder 1 is getting the complete input. Okay, these two input A1 and B1, it was present at t equal to 0, but it was waiting for the Cin. Okay, Cin, which came from your FA0, it was waiting for this carry input. So it came to this full adder 1 at t equal to 2 microsecond. Now at 2 microsecond, basically this full adder 1, FA1, got all the input. So this S1, it will be equal to 1 at t equal to 3 microsecond. Why? Because there is some propagation delay. So I will get this after 3 microsecond, this one. And this Cout will be generated after 2 more microsecond. That will be what? That will be, you can see, is 0. Now this is very good concept I am telling. Very good concept. Okay. So this will be what? This will be 0. But you can see what? Okay. So this 0. Now this 0. Okay. Sorry. This 0. Yeah, it's correct. So this 0 we got after how many seconds? We got after t equal to 4 microsecond. Okay. 4 microsecond we got. So at 4 microsecond, the input of all the full adder, means full adder 2, it is complete, all the inputs we have. So S2 will be equal to what? It will be equal to 0 after 5 microsecond, and Cout will be generated after 6 microseconds, so that will be 1. So this one we will get at, means full adder 3 will get this one at 6 microsecond. So at 6 microsecond, your input is going to be complete for this full adder 3. So S3 will be now equal to 0 at 7 microsecond, whereas the Cout will be generated after how much time? It will be generated after 8 microsecond. Okay, after 8 microsecond, what is happening? That this Cout will be generated, and that Cout will be what? It will be equal to 1. Okay, it will be equal to 1. Now tell me if this is clear to you or not. Is this clear? Is this clear? So whenever, remember, case 1, when some propagation delay is less than carry propagation delay. Okay, when some propagation delay, like in this case, some propagation delay is less than carry propagation delay, the delay, total delay in output, it is equal to n into carry propagation delay. Okay, so if I wanted to calculate this directly, here you can see n means what? N means number of full adder. So number of full adder is what? Number of full adder is 4. And carry propagation delay means what? It is your 2 microseconds, so 8 microseconds. After 8 microseconds, the complete output will be available. So complete output is all this, okay? Cout 3, S3, S2, S1, S0. So S3, S2, S1, S0, it was completely generated till 7th microsecond, but we needed to wait 1 more microsecond, that is up till 8 microsecond to get this C out. Okay, tell me if this is clear to both of you, Sri Hari and Surjit. Is it clear?
Clear, sir.
Okay. Now case 2. Okay, case 2. Assume some propagation delay is 2 microsecond and carry propagation delay is 1 microsecond. Now look what happens. See, we can even memorize the formula. It's nothing like that, but we need to understand what is happening actually. So look, at t equal to 0, I am applying all the input bits, but we don't have the subsequent scene. So let us see after how much time the total output will be generated. So at t equal to 0, I applied all the inputs. So the output S0, this will be 0 after how many microsecond? After 2 microsecond. But before 2 microsecond, you can see this carry out will be generated. This will be equal to 1 at t equal to 1 microsecond. And at 1 microsecond only, this full adder, it will get all the inputs. So it will take, see now, understand very clearly what is happening. So I got the complete set of inputs, the 0, 0, 1 at t equal to 1 microsecond. Listen very carefully. At 1 microsecond. So this S2, it will be generated after 2 more microseconds. So that is 3 microsecond. And this carry, it will be 0 at t equal to 2 microsecond. So at t equal to 2 microsecond, this full added 2, all the inputs will be available. Okay, at t equal to 2 microsecond, all the inputs are available. So this will be what? After 2 more microseconds, this S2 will be generated. So that will be 4 microsecond. But look, at third microsecond only, t equal to 3 microsecond, this C out will be generated. And at t equal to 3 microseconds only, all the inputs of this third full adder, it will be what? FA3, it will be available. So at 5 microsecond, I will have S3, but C out will be available at 4 microsecond. C out will be available at 4 microseconds only. Why? Because I require only 1 microsecond to see out. So in total, how much time do we require to get the complete output? We require 5 microseconds. Now, if I want to write over here, so we required what? Case 2. When some propagation delay is greater than carry propagation delay. So T delay means what? The time after which we get the complete output. So that will be what? That is coming out to be 5 microseconds. So the generalized formula over here is n minus 1 CPD plus SPD. Okay. So this is n over here is 4 minus 1 into 1 plus SPD is what? It is 2. So this is 3 plus 2, 5 microseconds. Okay. So this is what we get as an answer also. Okay. Now, why did we take in the last case this SPD? So some propagation delay. See, we got this carry means this carry before this sum. At the last stage, we needed to wait for this S3 because every other output like this one, this one, this one, and this one, everything was generated before this one. You can see at 4 microsecond, everything else was present, but only this one was not present. This is coming out at 5 microsecond. So for your last full adder, we need to wait for the sum to be generated. Previously, when your sum was less than carry, we never waited for the sum to come. But when sum is greater than carry, at the last full adder, we need to wait for the sum to get generated. So that is why n minus 1 CPD, CPD means what? Carry propagation delay plus SPD. So you can see, even if we directly put in the formula, we will be getting the answer. So there are two formulas that you need to memorize depending on the condition of sum propagation delay and carry propagation delay. Okay, where n implies your number of full adder. Any doubts, anyone? You can ask. Any doubt? Any doubt, anyone?
Sir,
Yes.
uh, before before opening this, it is given C out
Surjit,
is
I am not
already
able
one.
to hear you. I am
Then,
not able to hear you. I am not able to hear you. Your voice is breaking.
sir, am I audible now, sir?
Yes, yes, yes. Now you are audible.
Okay. So, sir, before performing this addition, if it is given C out is already 1, then we may consider the total propagation delay 3 microsecond, no, sir?
Pardon, I couldn't hear you. What you are saying? If C out is equal to,
Sir, the-
in which stage you are telling? Out of FA0, FA1, FA2, FA3?
yes, sir. Yes, sir, if it is given C out is already 1 before performing this addition, then only S1
Where
bit
C
is
out is
changing
given
from
as
0
well?
to 1, other is no change. So if it is given
Where?
in question, C out is already 1 for this configuration A and B inputs. So
In this,
we may write the final propagation delay is 3 microsecond or 5 microsecond.
I am not able to get what
I'm
you are asking.
actually
That you are telling that this
confusing.
C out is already present. This
Yes, sir,
C out.
C out is already 1 before
Okay,
performing this
already one.
addition. Yes, sir.
Okay.
And
So,
they
okay,
ask to
okay.
find
Tell,
the
tell me.
total delay. Yes,
No,
sir.
no. How will you get C out one before performing the operation? How do you know that? How do you know that? And if in the question it is given that C out you already know, C out you already
Yes,
know
sir.
that it is one,
Yes.
then what will be your time to get all the inputs? So it's okay. Then also you require S3, S2, S1, S0. See, all this C out, this one, this C out 2, C out 1, C out 0, these are
Yes, sir.
intermediate carries. Okay, these are intermediate carry. You cannot see what is this carry, but you know what this carry will be after this operation. This carry is the output
Yes.
carry, but all this carry, this one, and this one, these are your intermediate carry. Are you understanding the point? Are you understanding?
Yes, sir. These are intermediate. But after addition, the answer is
Your voice is
1
breaking.
carry
I
bit
don't
zero
know why.
zero one.
Your voice is breaking, Surjit.
Sir, am I audible
Can
now,
you?
clear, sir?
Yes, I guess there is some issue with your microphone. Means if you just go
Um,
out it's a
maybe
little
some
bit
network
farther.
issue.
Okay. Yes, now tell me.
Yes, sir. My doubt is before performing this addition, if C out is already 1 and all the sum bits are 0, means SC up to S0 are 0, then there is only S1 is changing from 0 to 1, so it will take only 3 microseconds. No? Means what I have to put actually in that case, 3 microseconds or 5 microseconds,
Okay, so
because
I
only one
understood
bit
what
is
you are.
reflected.
Okay, okay, okay,
Because
okay,
these two
okay.
things are
So you are
confusing
okay,
between these two
okay. I
sometimes.
understood what you are telling now. Now I understood. So you are telling that, sir, this is 1, this is 0, this is 1, this is 0, 1. You are telling me that, sir, only this bit is changing. Okay, where is this bit? So this is 1. Okay, this bit is changing and none of the other bits are changing over here. But if you see, this is a ripple carry adder. See, you know basically that over here it is 0, but this full adder, it does not know that what will be the carry generated. Or you can see from here 1 is coming. Previously also it was 0. You are thinking that this was 0. After t equal to 1 microsecond also this is 0, but this is not the case. When you switch on the circuit for the first time, this full adders, they don't know actually what is the carry. What is the carry? They actually don't know. You are confusing with one of the question of this thing. What? 2014 there was this question. Okay,
Yes,
there
sir.
was this question.
Yes, sir,
Yes, I
exactly.
know
Yes,
that
yes,
there
sir.
was no change in states. Okay, there was no change in states. But that, if that question, if you see, so I know that question also means there was this full adders given, and means question like this only it was there, and there was that one point where you're actually not changing the carry. Okay, actually not changing the carry. So in that place you were applying the input, but that was parallel addition going on. Have you seen the circuit of that question? Have you seen the question, that question?
Sir, yes,
So if
sir, I have
means
to find actually.
Okay, just wait a minute, okay.
Sir, only the
Okay, so first let us calculate for this one. Tell me. Calculate for this one.
one.
Can't hear you guys. There is some network issue.
195, sir.
Okay, so look over here. A 16-bit ripple carry adder is realized using a 16 identical full adder as shown in the figure. Figure I haven't taken. The carry propagation delay. So carry propagation delay is equal to 12 nanosecond, and your sum propagation delay is equal to 15 nanosecond. So they are asking about what will be the worst case delay. Worst case delay. So worst case delay means what? That each of the full adder is suffering from delay. So this is where means I should have told you that all the full adders are suffering from delay. Now you were correct, Surjit. In this case, in this particular case, you should have written 5 microsecond. Why? Because few of the adders, they were not suffering from delay due to the fact that their states were not changing, like over here. Okay, like over here it was 0 previously also, 0 here also. So this, it would have got its output at 1 microsecond only. I should have told you this. What is worst propagation delay is that all the full adders are suffering from delay. Okay, all the full adders are suffering from delay. Understand this. So this is what is asked, and this will be only asked in HAL. Okay, so if you see, carry propagation delay is 12 nanosecond and your sum propagation delay is 15 nanosecond. So when sum is greater than carry, our formula is what? N minus 1 into C into S. So N is what? 16 bits. So 15 into carry propagation delay is 12 plus this will be what? So 15. So 15 into 12 is 180. 180 plus 15. So that is 195 nanosecond. So 195 nanosecond is your answer. But this question, you were talking about this question. So over here means I only have made a mistake over here, that I shouldn't have taken this particular example, because in this particular example, all of the full adders are not suffering from delay. Okay, all of the full adders. So Surjit, you were talking about this question only, na? Surjit?
Yes, sir. Yes, sir. Yes,
This
sir.
particular question. So in this particular question, so this is what has happened over here also. Okay, this is what has happened in this question also. So I will make you understand. See, this concept will not be asked in HAL. So I have made a mistake over here. So I will try to make you understand this concept, and then we will move to sequential circuit. So for this particular example, this is wrong. See, if I had taken one example like this, worst case delay means all the full adders are suffering from delay. Means all the full adders are generating C out. That is what we meant by worst case delay. Worst case delay means what? All the full adders, they are generating carry out. Means like something like this. Okay. When we have something like this, so what will happen? Over here, this will be 0. See, 1 is generated as carry. Again, this will be what? This means over here, I could have taken 0 also. You might be thinking, why have I taken like this? You could have taken 0 also. Even here also, I could have taken 0. So you can see this will be what? This will be 0. Again, carry will be 1. Over here, you can see what? Again, this will be 0. Carry will be 1. This will be 1. Carry will be 1. So if I had taken something like this, then you can see each of the subsequent stages, I am generating a carry, due to which I am getting what? I am getting worst case delay. But in our particular case, look over here, what I had taken, 1. So try to understand this concept. This will not be asked in gate. Okay, but still, means for understanding this concept, now again I have to go in very depth of propagation delay. Okay, so what do we mean by propagation delay? First tell me that. What do we mean by propagation delay? Surjit, you only want to say? So you can say, what do we mean by propagation delay, and when do we see the effect of propagation delay? First tell me that.
Sir, the maximum time required for output can be stable for the given input.
Output to be stable for a given input. Okay, fine. Suppose this is your AND gate. It has 2 nanosecond delay. Okay, 2 nanosecond delay. Okay. Now, assume that this has 2 nanosecond delay. So the first condition for delay to happen is that, so output will be 1. Now I never told you when this is starting. So let me assume that I am applying this input at t equal to 0 nano, means 0 seconds. Okay. So that means what? Before 0 second, that is at t equal to 0 minus, what was my input? My input, it was not applied, as this is binary. So you can assume what? You can assume it to be 0. Okay, you can assume it to be 0 because I told you inputs have been applied at 0 microsecond. So at 0 minus, this was 0 0 and output was 0. Now look very carefully at t equal to 0. For this particular case, I am telling that this AND gate, I am applying input as 1 1. So after 2 nanoseconds, my output will be 1. So this is what Surjit you said, that for your output to get stabilized after some time, that is known as what? Propagation delay. This is very correct. But assume instead of this case, if I had assumed at t equal to 0 minus, my inputs were 1 1. I am assuming like this. I am assuming at t equal to 0 minus, my both the inputs were 1 1, output was 1. Then at t equal to 0, I applied my input as 1 1. So still output hasn't changed. So for propagation delay to occur, remember this, for propagation delay to occur, input should make a transition. Input should make a transition. Okay, transition. Either it should change from 0 to 1 or it should change from 1 to 0. Okay, so always input should make transition for propagation delay. Tell me if this concept is clear or not. Tell me if this concept is clear or not, everyone.
Please.
So now
Yes,
look
sir.
very carefully what is happening over here at this place. So this is 1 1, this is 0 0, this is 1 1, and this is 1 0. So at t equal to 0 minus, I am telling about t equal to 0 minus. Okay, t equal to 0 minus. So let me color code it also. I am applying everything at t equal to 0 minus using black color. Okay, so at t equal to 0 minus, everything was 0 0 0 0 0. I am assuming that everything, your adder was resetted. So if everything was 0, so this C out will be also 0 0 0 0. Sum will be also 0 0 0 0. Everything is 0. Then suddenly at t equal to 0, I am applying this. Now look very carefully. Now for the subsequent stages, let me write it using this color. Okay, subsequent stages. After 0, t greater than 0, everything I will write using this color. See what I told you, for propagation delay to affect, what should happen? Your input should make transitions. So in the second case, what I had assumed, some propagation delay to be 2 and carry as 1. And carry propagation delay as 1. So now listen very carefully. So look, at t equal to 0, this is already 1 1. So sum is making, as you can see, look over here very carefully, as your inputs are making transition, any one of the input is making a transition, so obviously your sum is going to change. So this will be what? This is 1, and due to this, your C out is also changing. Previously it was 0, now it is changing state to 1. Now when this is 1, you can see, so this was generated after how many nanosecond? Sorry, here it was microsecond. After 2 microsecond, this was generated, and this was generated at 1 microsecond. So this sum, it is being generated at what time? It is being generated at your 3 microsecond, and this zero was already present over here. Okay, it was present from t equal to 0, and still as C out is not changing due to the effect of this input, because input has also not changed. So Cout is also not changing. So this is remaining 0, and this 0, this black color 0, it was available from t equal to 0 minus. Okay, so this was available from t equal to 0 minus. But look over here, this input was applied at t equal to how much nanosecond? Sorry, nanosecond, I am continuously telling. This was present at t equal to 0 microsecond. As your this full adder, it had your C in present from your 0 minus time. So here sum is going to change. Obviously sum is going to change by 1 plus 1, sum is 0. Okay, previously also it was 0 plus 0, it was 0 only, you can see. Now also it is 0. So this over here, this S2 was present from 0 microsecond. Why? Because over here you can see there is no transition. Previously also it was 0, now also it is 0. So there is no transition over here. But look at Cout. 1 plus 1, sum is 0, but Cout is 1. So when is this Cout being generated? This Cout is generated at t equal to 1 microsecond. Why? Because all the three input, this was the input, all the three input was available at 0 microsecond. So after 1 microsecond only this was 1. Tell me if this concept is clear or not.
Clear, clear.
Shriyari, Surjit, this was your doubt, so I need to know. So this is gate type of question. This won't be asked in your HL exam. Okay. Surjit, is this clear to you? Okay, fine. So he is not responding. So look, these three inputs were available at 0 microsecond. See, because this scene, it hasn't made any transition. So this carry out is generated at 1 microsecond, whereas this sum is already present at 0 microsecond. So at 1 microsecond, look, this FA3 has all the inputs present at 1 microsecond, because this red color inputs, it was present at 0 microsecond, and this carry, it is generated at 1 microsecond. So S3 generated over here, this will be what? This will be 1. Okay, and Cout over here is what? This is still 0. Previously also it was 0. Now also it is 0. So now look for this question, for this particular question, your propagation delay, you can see all the inputs all the output S3, S2, S1 and S0, it has been generated within 3 microseconds. So for this particular question, your answer will be 3 microseconds. Why? Because all the full adders were not suffering from delay due to the fact that all the full adders input were not making a transition, and when it is not making transition, so propagation delay will not happen. Okay, is this clear? Shriyari, did you understand this concept?
Clear, sir, clear.
Okay, so I want you to solve this question at home. Okay, so take a screenshot of this question. So this question is based on this concept only. So they have done nothing, means they have just shown this full adder and they have broken this, means XOR, XOR and OR gates they have given. So first thing is you need to calculate some propagation delay and carry propagation delay, first concept, because they have individually given for a full adder what are the propagation delay of each of the components it has been given. So first you need to calculate sum and carry propagation delay, and then you need to calculate after how much time all the outputs you are going to get. Okay, so this is your homework. So this will not be asked in HAL, but this might be asked in your gate questions. Okay, so this is very good concept. Okay, so let us start with sequential circuits now. So what do we mean by sequential circuits? So in our last session, we have discussed about combinational circuit. So combinational circuit is basically a circuit in which what we have, we don't have any memory element, If we don't have any memory element, that means what? Your present output is a function of present input. Okay, so this was what? This was your combinational circuit. Okay, now in sequential circuit, what happens? Your present output is a function of present input as well as past output. So this is what? This is your sequential circuit. So whenever we require past output, so we require something actually to store the past output. Okay, to store the past output, we require something. So that is what is known as sequential circuit, where your present output, it depends on present input as well as past output, and for storing past output we require some kind of a memory element. Okay, so in sequential circuit, along with the combinational, so sequential circuit is actually combinational circuit plus memory element. Okay, so now look, so Surjit, yes, there is some net issue at your end, I guess. Okay, so sequential circuit, what I was telling, that it is basically a circuit which is a combination of combinational circuit as well as your memory element. So one of the simplest sequential circuit is a latch. Okay, latch. So latch is what? It is a cross coupled NOR gate or NAND gate that we are going to see. And a flip flop is basically a latch that has a clock circuit. So why do we add clock circuit in any of the circuit? Clock. Why do we add a clock? For synchronizing all the circuit elements. Okay, for synchronizing all the circuit elements that we are going to see at the moment. Okay, so any flip flop, it has two stable states we are going to see. Okay, it has two stable states. Whenever, yes, tell me. Hello, anyone have any doubt?
No, sir. Actually, my network issue is very happening.
So I explained your concept. Okay, so you need to watch the recording. Okay, so I explained
Yes,
the concept.
sir,
So
yes,
you
sir,
are correct.
definitely.
In this question, your answer was 3 microseconds. Okay, so this question
Okay,
I gave as
sir,
homework.
I'll check that.
This question I hope means you have solved this question. I'm hoping this. Okay, so even this part
Okay,
skipped my mind, that in this example that I had taken, there was no worst case delay. So I should have kept that thing in the mind. Okay, and I should have explained, but it skipped my mind. It's very good that you reminded me and we discussed this concept. Okay, so this is very good. This might not be asked in your HAL. HAL directly they will ask you questions that are put the formula, get the result type. So they will always ask you about worst case delay only. So worst case delay, the formulas are this one. When your sum propagation delay is less than carry propagation delay, and in case 2, sum propagation delay is greater than carry propagation delay. Okay.
okay, sir. Means, sir, in worst case delay, if they ask worst case delay, we don't look into deeper. Just we have to use the formula,
No,
sir.
no, no, no. You don't need to see. Whenever they haven't specified any input, like A is equal to 1101, B is equal to 0101. If they haven't mentioned input like this, you don't need to check. You will always assume that worst case delay is happening. But if input is given, then you need to check in which of the subsequent stages of full adder, sorry, in the subsequent stages of ripple carry adder, which of the binary, means which of the full adders are suffering from delay, or which of the full adder has a transition in inputs. Whenever they give you input like this, see, in this question also they gave you input over here. externally. But in this question, look, there is no mentioning of input, and they have directly told also worst case delay. Okay.
Okay.
So whenever
Okay.
input is
This is the thing.
given, you need to check. And whenever inputs are not given, you directly need to see the sum propagation delay, carry propagation delay. And if sum is greater than carry or carry is greater than sum, accordingly, you need to decide which formula to apply and you need to get the result. That's it. But if input is given, you cannot apply formula and get the result. Then you need to check all the subsequent full adders in which of the full adder your stages are changing, and where it is not changing, then you have to decide.
Oh,
That is very good.
okay,
That
okay. So now, yes, sir.
now it's clear.
Nobody told me this before. Yes, sir. Yes, sir. Nobody actually told me this. That's why I'm confusing actually this thing. Now it's
Okay,
clear, sir.
so it's okay. So if you had studied for GATE, I would have solved this question. But still, as you mentioned this question, so that is very good. Okay, even it skipped my mind also. Okay, if you hadn't told me, I would have considered worst case delay. So that is very good. Means everything, what happens, we remember everything. Okay, but sometimes what happens, we
Yes.
don't take it like that. So as you told, I suddenly remembered, yes, you are correct, that over here I have taken a particular set of input, and due to that, your all the inputs are not changing. So I am hopeful that you have understood what I have explained. Okay.
Yes, sir.
So
Yes,
now
sir.
you
Sure.
won't be facing any difficulty in such kind of questions, delay type of question. Okay. So now let us
No,
talk
sir. No.
about
Yes.
sequential circuit. Sequential circuit. So what is a latch? Everybody knows that latch is a cross-coupled gate. Okay, cross-coupled gate. So in a cross-coupled gate, basically one of the output of this NOR gate, it is connected to the input. Okay, so output of the first NOR gate is connected to the input of the second NOR gate, and output of the second NOR gate is connected to the input of the first NOR gate. Okay, and this is what? This is your NAND latch. This is your NOR latch. This is your NAND latch. So I am not going in very much depth over here, that what do we means, why this latch it is used as your memory element and all those things. I am not going. Okay. So look over here. I have taken one of the simplest latch, that is your SR latch. Okay. And I have constructed it using your NOR gate. Now there are various type of state. Okay, various type of states of latch or flip flop. Okay, so very quickly let me decide output states to be precise. So first is what? First is set state. Set state means what? See, this is your, okay, let me first define what are these. So over here, this is your set input, this is your reset, or at the moment, since I had written SR, so let it be. At the moment, you can consider it as AB also. Okay, if you are not comfortable with what is set, what is reset, so it's okay. You can even consider this as AB. Okay, let me assume this is A, this is B. So these are your input. Now this QN complement and QN, basically these are your past normal output. This is your past, past complemented output, and this is your past normal output, and this is what? This is your present. Why present? Because Qn plus 1, okay, n plus 1, we take it as present. So this is your present complemented output, and this is what? This is your past complemented output. Okay, so based on this output, we have what? We have different states of the flip flop. So first is what? Set state. In set state, Qn plus 1 is 1, and Qn plus 1 complement, it is equal to 0. Now obviously these two are always going to be at a different state. Why? Because both of them are complement of one another. So it cannot be like both of them are 1 1 or both of them are 0 0. So whenever that happens, when both of them are 1 1 or both of them are 0 0, for that also we have a particular case. But we get your output. So basically I am classifying the output states. So output state will be known as set state when your Qn plus 1 means normal output is 1 and complemented output, present complemented output is 0. Next is reset state. So reset state means when your normal output is 0 and complemented output is 1. Third is hold state. Hold state. So in hold state, normally whatever is your present output is same as your past output. And the last state we have is what? We have is invalid state. So in invalid state, what happens? This Qn plus 1, it is equal to Qn complement, or you can even say that it is equal to Qn plus 1 complement. But we know what? Such kind of case cannot happen due to the fact that as they are complemented state of one another. So this is why this is known as, this state is known as what? This is known as your invalid state. Tell me if this is clear or not. Is this clear? Okay. One more state we are going to see, that will be toggle state. Okay. So in toggle state, what will happen basically? That Qn plus 1, it will be equal to Qn complement, or even you can say Qn plus 1 complement will be equal to Qn, any one of the following. Okay. So this will be toggle state. This we are going to study later on when we see your T flip-flop or JK flip-flop. At that time we are going to see this state. At the moment we are going to see this 4 states of flip-flop. Okay. Okay, so copy it down very quickly. I will be erasing this part because I require this thing.
So
Copy
toggle
it down quickly.
it can possible in latch also.
No. Toggle state, it will not be possible. So that is why I told you this we will see in JK flip-flop and T flip-flop, not over here. But as we have an output state, so I have discussed now.
Okay.
Okay. Okay, so now let us see what do we mean by this. So I told you at the moment that if you don't know what is a set input, reset input, let me assume it as AB. Okay. See, when you take A as 0, B as 0. So let me use green color. So when you take A is equal to 0, B equal to 0, what will happen? See, in NOR gate, if one of the input is 1, it doesn't matter what is the another input. Immediately we can say that output will be 0. Okay, it doesn't matter. If one of the input of NOR gate is 1, so we can say output will be 0. If one of the input is 0, then we cannot make a comment what will be the output. Then we need to know basically what will be this input. Okay, so remember this, whenever in your NOR gate one of the input is 1, immediately we can say output will be 0. But out of the two inputs, if one of the input is 0, we cannot make a comment about the output of NOR gate. So this you should understand. So look over here, A and B both are 0. So A is input of this first NOR gate, and B is the input of the second NOR gate. So both of them are 0. So basically I need to see what is your another input of both the gates. So for this you can see it is Qn, and for this one it is Qn complement. So if I pass it from here, what will happen? This will be Qn plus 1 will be equal to Qn, and Qn 1 plus 1 complement, it will be equal to Qn complement. Okay, it will be equal to Qn complement. So this is known as your hold state. Okay, this state is known as your hold state when you get both the inputs of your NOR SR latch. If you put it as 0 0, you will get what? You will get hold state. Okay, so this is your hold state. Now look, if you put A equal to 0, B equal to 1, what happens? See, the moment you put B equal to 1, okay, so that means one of the input of this second NOR gate is what? It is 1. So immediately this will be 0. If this is 0, this 0 will be latched to this. So this will be 1. So you can see complemented output is 1 and normal output is 0. So this is known as reset state. Okay, reset state. Now look, if I put A equal to 1, B equal to 0, so A1, B0. So the moment I put one of the input of this first NOR gate as 1, immediately this will be 0. If this is 0, this 0 will be coupled over here. So this will be 1 now. Okay. So you can see this Qn plus 1 is 0 and this is 1. So 1 0. This we known as what? This we know as set state. Now look, the last case is what? Both the A and B, it is 1 1. So now what happens if I put both of them 1 and 1? So immediately output of both the NOR gate is 0 0. Now this is not possible. Why this is not possible? Due to the fact that both of them are complement of one another. So this is known as invalid state. Now, why did I mark? Suppose if you don't know which of them is set state, means set input and reset input. So now look very carefully. So when which of the input, if I apply 1, your normal output goes to high state. I am asking which of the input out of A, B, if I apply 1, your normal present output goes to high state. You can see A. Whenever if you see, if I put A equal to 1, except this case, because this is what? This is invalid state. When you put A equal to 1 and B equal to 0, at that time your latch goes to set state. So that means this A input is set, and look which of the input, if I apply 1, your latch goes to reset state. You can see when I apply 1 in B, so that means this B is reset. So this is set input, this is reset input. And one more thing, in any of the latch, suppose if I have a latch like this, now you cannot go and check, means by applying all this truth table you cannot check. Okay, suppose if I give you that this is Qn plus 1 complement, this is Qn, sorry, if this is Qn plus 1, this is Qn plus 1 complement. Always remember, in a NOR latch, the set output will be opposite to your complemented present output. So opposite to this is what? This input. So this will be set, and if this is set, obviously this is going to be reset. So I always say all my students to remember it like this. In NOR latch, Opposite to complemented, we have set input. That's it. Now if you know set input, obviously another input will be reset. Is this clear, everyone? So this is the concept of SR latch. Now let us talk about NAND latch. Sorry, this was NOR latch. Now let us talk about NAND latch. See, in NAND latch, there is a little bit different concept. Okay, why? I will tell you. See, previously when we had studied NOR, I told you that in NOR gate, whenever it is 1, it doesn't matter. Whatever is your input, output will be 0. So NOR has more affinity towards 1. Why? Because if it is 1, directly your output can be 0. So NOR, more priority is given to 1 in NOR gate. But in NAND, if you see, so this concept also means it is a little bit tricky, but usually I don't teach this concept. Okay, so you can see, I will just tell you, but it's okay. Okay, if you are not able to understand, it's okay. Okay, so look, if your input is 0, one of the input of NAND gate is 0, it doesn't matter that what is your another input, directly this will be 1. Okay, output will be 1. But if one of the input is 1, now you need to see what is your another input, then only you can comment about output. So your NAND gate, more priority is given to 0. Okay, more priority is given to 0. So that is why you can say that this latch is active high latch. Now usually I don't tell this concept. Okay, let us skip this. Let us skip this. In NAND, we basically have more priority towards 0, but it's okay. Even if we don't understand this, I will show you one more concept over here, with the help of which you will be able to understand. Okay, so look very carefully. But just remember this thing. Okay, just remember this thing, it will help you. We are not studying for gate, so even if we avoid all this, it will be okay. So now look very carefully. Let me assume this is A, this is B. Okay, so at the moment I am telling that you don't know which is set, which is reset. So if both the input are 0 0, look very carefully, if both the inputs are 0 0, what will happen? As this is your NAND gate, immediately both the outputs is going to be 1 without even looking into your the other input, I can say. So this is 1 1. So this is what? This is invalid. So in NOR, I told you 1 has more priority. Okay, so 1 is basically the input over here. Input 1 means you are giving input. In NAND gate, 0 means you are giving input. But it's okay, even if you don't want to understand this, you can still solve questions. So this is very higher level concept, that in NAND latch, basically giving 0 means that you are giving input. Okay, you are giving input. So if you study old textbook, over here we don't have set and reset. Here we have set bar and reset bar, due to the fact that in NAND gate, applying 0 means that you are applying input. But it's okay, means if I do this, it will be very complex for you guys to understand. So it's okay, let us still have this concept. Whatever we have studied, we will see. So look, 0 0 means what? This is going to invalid state. Previously in your NOR latch, whenever we applied 1 1, we were going to invalid. Now for this case, whenever we apply 0 0, we are going to invalid state. Okay, so now look, what happens if I apply 0 1? See, if you apply 0, 1, so this will be immediately 1. If this is 1, so 1 into 1, this will be 0. So you can see Qn plus 1 is equal to 1 and this is equal to 0. Okay, this is 1, this is 0. Now look over here. Okay, over here you see when you apply 1, okay, when you apply 1 at A, when you apply 1 at A and 0 at B, what will happen? If this is 0, this will be 1. Okay, means have I done some mistake in the last case or what? This was 0, this was 1. Okay, fine. So now A is 1, this is 0. So in the last case, what I had taken? Okay, so this should have been 0, 1, na? Sorry. Here I have made one mistake. A is 0, B is 1. So I had taken the opposite case. So A is 0, B is 1. So when this is 0, so this will be 1. So this will be 0. So normal output is 0, this is 1. So now look. See, if I apply 1 over here and 0 over here, so this will be 1, this will be 0. So write it 1, 0. And when you apply both of them 1, 1, so when you apply both of them as 1, 1, so this will be what? Over here we have Qn complement, sorry, Qn normal Qn and Qn complement. So this will come over to here, Qn complement, and this will be Qn. So we will be getting Qn and Qn complement. So this is giving you your hold state Qn complement. Now I told you this concept. What? That look at that input. When you apply it 1, you go to set state. So you can see over here that when you apply 1 at A, you are going to set state, and when you apply 1 to B, you are going to reset state, because this is reset state, this is set state, and this is your hold state. So that means what? Your A is your set input and B is reset. So always remember, even in Nand Latch, your set input is directly opposite to Qn plus 1 complement. But in old textbook, I am telling you this repeatedly, in textbooks, in old textbook, you are going to find for NAND gate, set bar will be opposite to Qn plus 1. Because why? I told you in NAND gate 0 has more priority, and 0 we usually describe it with a complemented term. So in old textbook you are going to find this, but if you take this into consideration, solving questions will be very, very tough, very, very complex. So even I took a lot of time before teaching to understand this concept. So it is rather what we do, we keep it in this term only, that for NAND latch also set input occurs opposite to complemented. You can see directly opposite complement we have set. Tell me up to this point, is it clear, everyone? Is this clear? Any doubt?
Clear.
Yes.
Any doubt, anyone? Okay, fine. So now let us see what? Let us see SR flip-flop using NOR latch. Now what is flip-flop? Basically, you can see over here, suppose if I have multiple latches, what I am telling, if I have multiple latches in a circuit, okay? So when we have multiple latches, the output produced by them, see, now we cannot assume that all the latches are what? All the latches, they have been provided input at the same time. We cannot assume. Some of them might get input at a later stage due to the fact that there is some propagation delay, or even if you know the concept of fan in and fan out, okay? So the input they might be getting from some gates which have your different propagation delays. So there might be what? That even if we have identical latches, output will not be produced at the same time. So for synchronization, what we do, we have one clock circuit. So clock is basically a square waveform that synchronizes your circuit. Okay, so even in your laptop you might have seen clock frequency. Higher the clock frequency, better is the circuit. Why? Because if clock frequency is high, what will happen if clock frequency is high in a laptop? What will happen?
Timing and everything.
Speed will be increased.
Why speed will be increased? Why speed will be increased?
The instruction cycles and
Yes, very good. So clock frequency, basically what it will do, if you have a clock frequency that is very higher, the number of instruction that is executed in one time period, that will be very number of means the time period of each execution, it will be small, because in one clock cycle execution is taking place. So if you have 1 gigahertz of clock frequency, so that means for executing one operation you are requiring 10 to the power minus 9 second, or sorry, 10 to the power minus 9 nanosecond I have written, 10 to the power minus 9 second or 1 nanosecond. So your execution becomes very faster, or in a single second you can perform 10 to the power 9 operations. So that is a very high number. Okay, so that is why clock frequency higher is desirable. So clock is basically a circuit. It synchronizes your all the other latches, or you can say flip-flop. So now look very carefully, how do we implement SR flip-flop using NOR. So once again I am telling, if you don't know, you can consider this input as A and this input as B. Now clock, it can be either 0 or it can be 1. So when this is 0, when clock is 0, it doesn't matter whatever is S or R. What will happen if clock is 0? This is AND gate, okay? So this output will be 0. And if input to your SR latch, if it is 0, that means what? That means this will be in hold state. Okay, this will be in hold state. So SR, it doesn't matter whatever is your input, means over here I have taken actually AB. So later on I am going to tell you how to take S and R. So whatever is the input, it doesn't matter. So this means don't care. Okay, don't care. It can be 0, 1, anything. Output will be always in hold state. So this is hold. Now assume if your clock is 1 and first your A is 0, B is 0. Still for this case, if A is 0, B is 0, as this is AND gate, so again 0, 0, we will be getting 0 over here, 0 over here. So whenever your input to NOR latch is 0, 0, we have hold state. So this is again hold state. Next, if I take 0, 1, so look, if A is 0, so obviously this is going to be 0. And if B is 1, so this is 1. So if this is 0, this is 1. So what we know, immediately this will be 0 and this will be 1. Okay. Now, why this happened? If this is 1, sorry if I have done something wrong. No, this is okay. Sorry. Let me do it once again. Today I am struggling a little bit due to the fact that I am having cold. Okay. So look, if I take 0, 1, what will happen? If this is 1, immediately this will be 0. And if this is 0, so both of them are 0, 0, this will be 1. So write this. This will be what? Complemented is 1 and normal is 0. So this is reset state. Okay, reset state. Next is what? If I take A as 1, B as 0. So A1, B0. So if I take that, this will be 1, this will be 0. So if this is 1, immediately this will be 0, and if this is 0, okay, so this will be latched over here, this 0 will come over here, so immediately this will be 1. Okay, so what we got? Complemented as 0, normal as 1, so this is set state, and last is 1 1. So applying 1 1, what will happen? So if we apply 1 1 to A and B, you can see input to this latch will be 1 1, and we know what, whenever we apply to NOR latch 1 1, we get what? We get 0 0, and that is invalid state. This is not possible, so this is invalid. So this is what? This is the truth table of your SR flip-flop. Now suppose if, means I have written over here, now suppose if we didn't know out of this which is set, which is reset, so look for the input, when we apply 1 to it, we get set state. So you can see whenever I apply 1 to A, okay, and 0 to B, I am getting what? I am getting set. So obviously A is set, and if A is set, that means B is reset. So you should be knowing that in SR flip-flop also, S is opposite to complemented output. So till now we have studied what? We have studied SR latch using NOR, NAND, SR flip-flop using NOR. So in all the three places, set input is opposite to your complemented output. So this is going to help you in a lot of questions where S and R will not be marked for you. Okay. So up to this point, is everything clear? Everything, is this clear? Okay, fine. So now look, in the next case, let us solve SR flip-flop using NAND latch. Okay, in NAND latch. So same again, if clock is 0, now here you are going to see some difference. So look very carefully. See, in SR flip-flop, when we used NOR, we had AND gate over here in clock. But in NAND, we have NAND only in clock. So when we apply clock as 0, what will happen? If we apply clock as 0, so this will be 1, this will be 1. So if these two are 1 1, so what will happen? What we will get? So yes, so this will be 1 1. So when we apply 1 1, what will happen? We know what, that it will go in your hold state, because we know what, in NAND applying 0 corresponds to applying input. So applying 1 1 means what? That we are basically in your hold state. Okay, so it doesn't matter whatever input we apply, it will be always in your hold state. Now if clock is 1 but S is 0 and R is 0, so what will happen? See, if you apply 0 0, so when you apply 0 0, so this will be again 1, this will be again 1. So to a NAND latch, applying 1 1, it always does what? We are still in your hold state, because in NAND latch applying 0 corresponds to applying input, so we haven't applied input yet. Okay, so this is also hold state. And if you are not able to understand, you can take help from here. Okay, so where have we done? Have we done some mistake or what? 0 0, yes, over here you can see 1 1. So whenever input to SR latch, SR NAND latch is 1 1, so we get hold state. Okay, so when we apply 0 0, we get 1 1 over here. So this is your NAND latch, input to NAND latch. If it is 1 1, that means we are in hold state. Now look very carefully. If clock is 1, okay, clock is 1, so here I should have taken it as A and this as B. So this is A, this is B. Okay, so if A is 0, B is 1. So what will happen? Over here, one of the input of the NAND gate is 0. So immediately this will be 1 and clock is 1. So this will be 0. So if this is 0, what will happen? If one of the input of NAND gate is 0, immediately output will be 1. If this is 1, this one will be latched over here and this will be immediately 0. So Qn plus 1 is coming out to be 0 and this is coming out to be as 1. Okay. Now look, if I apply A equal to 1 and B equal to 0, what will happen? See, A equal to 1, B equal to 0. So if this is 0, this will be 1 and this will be 0. So if this is 0, obviously this is going to 1 immediately and this one is going to be latch over here. So this will come out to be 0. So this will be 1 0. Okay. So this was your set state, this is your reset state, and this two are your hold state. Now the last case is what? When we apply AB both as 1 1. So if we apply both of them as 1 1, so output of the clock will be 0 0. And we know what? When we apply 0 0 to both the input of NAND, we get invalid state. Both of them will be 1 1. So this is invalid.
So I think we are having some mistake in that set and reset.
Why?
Like in the
Okay,
Q1.
okay. So I have written the opposite thing. So this will be what? No, this will be reset. Sorry, means I have made some mistake. What? Yeah, this
Right.
will be reset. Now
Right,
it is
right.
correct, and this will be set. Okay,
Right,
so
sir.
now it's correct. Okay, fine. So now we have seen what? We have seen SR flip-flop using NAND latch, SR flip-flop using NOR latch. Now see very carefully. If we don't know out of A and B which is set, which is reset, means I have marked over here because I know. So look, if we don't know, look for the input which is making set. So you can see when I apply A as 1, I am going to set. When I apply B as 1, I am going to reset. Okay. So reset and set state you will get when you apply any one of the input as 1 and another as 0. Now don't think that if we means over here also this is 1 1. So how can you get reset or set when you apply both the input to 1 1? You won't be getting that. Okay. So now look, when you apply A as 1, you are getting set. When you apply B as 1, you are getting reset. So A is set and B is reset. Now this is very important. Only in case of SR flip-flop using NAND, your set input is opposite to normal output. In all the other three cases, set input is always opposite to complemented. So remember this. Means you will see maximum number of times set and reset has been given in the question. But few questions of gate or good questions of PSUs also you will see that they will not mention which input is set and which is reset. By looking in the output you need to see. So if nothing was mentioned over here like this, so immediately you see which of the output is complemented, which is non-complemented. So as this is SR latch using NAND, so opposite to normal output you will have set, and means if one of the input is set, remaining will be reset. So I have done what? I have constructed everything in terms of set input only. So if you construct latch, so in latch you can construct it using NOR or NAND. So S input is always opposite to complemented in both the cases. So if you ask someone, they will not be able to reply, okay, that how they know basically which input is set, which is reset. In flip-flop we have again two, okay, SR flip-flop I am talking. So again using NOR and NAND. So in NOR, S is opposite to complemented output. In NAND, only in this particular case, S is opposite to normal. Okay, S is opposite to normal. Now, due to the time constraint, I cannot show actually that why over here we have this normal and why in the rest of the three cases you have complemented, because I need to finish the syllabus also of this one. So that is why I am not discussing all those things, not going into very detail, or else if we go in depth you will even understand why over here set is means opposite to this normal form and why over here set is means opposite to complemented form. Okay, so let us not discuss that. Now let us write the truth table of SR flip-flop combinedly. Okay, truth table of SR flip-flop. So how do we write the truth table of SR flip-flop? See, simultaneously we are going to write NAND and NOR. Now in question they will tell you that a SR flip-flop has been constructed. Now they won't say it is NOR or NAND. So you should have a combined truth table. See, I have constructed truth table for SR flip-flop using NAND, using NOR. So I need to combine these two tables. Okay, I need to combine these two tables. So look very carefully. Whenever clock is 0, it is hold state. Okay, so clock 0, it doesn't matter what is S, what is R, always you are in hold state. Now look, when clock is 1 and set is 0, reset is 0 in both the case, what will happen? See, this was set, this was reset. Okay, in both the cases, if you see, when it is 0 0, again it is in hold state. So again this will be in hold state. Now look, clock 1, set 0, reset 1, what happens? This case, so this is reset 0 1, and over here this is also 0 1. So that means what? In both the cases it is reset. So I am going to write it is reset. Now look, clock 1, set 1, reset 0. What happens in both the cases? So this case I am talking about. So 1 1 0, it is set state, Qn1, Qn0 in case of NOR, and even in case of NAND you can see that it is 1 0. So this is set. Now the last case is very good, when you have both the inputs as 1 1. So look over here, when you apply 1 1 in case of SR flip-flop, you are getting 0 0 in case of NOR SR flip-flop. Okay, but in NAND you are getting 1 1. So what should I write over here? What should I write? See, in case of NOR, it is 0 0. In case of NAND, it is 1 1. Okay, in case of NAND, it is 1 1. So what should I write over here? So it can be either 0 0 or it can be 1 1. So simply, if I want to write, I am going to replace it with don't care. Okay, don't care. Yes, so this will be what? This will be invalid state. So this is the truth table of SR flip-flop without knowing that whether this is NOR or NAND. If it is NOR, so over here you will get 0 0. If it is NAND, you will get 1 1. Okay. Now let us discuss characteristics table. So before going into characteristics table, let me tell you what is characteristics table. So characteristics table is basically the combination of all input along with your past state to get the present state. So this was your past state, this is your present state. So characteristics table is basically all the combination of input and all the input and past state to get our present state. So all the combinations of SRQN will be what? Okay, so this is what? This is your characteristics table. So in SR flip-flop, whenever we have 0 0, we have hold state. So hold means what? You basically hold the past output. So here you can see the past output is 0, so this will be 0. Again, when SR is 0, look at this table continuously. So you have hold state. So now this time your past state was 1, so you are going to mark 1. When your set input is 0, obviously your output is going to be 0. So in these two cases, you have your set. Now in this two case, you can see set input is 1, reset input is 0. So this is your set case. Obviously output is going to be 1 1. Now in this two case, look, it is 1 comma 1. So whenever it is 1 1, we have invalid state, and for invalid state, you can see your present output is don't care. So put don't care over here. Okay, so this is your don't care. Now we need to get what? Characteristics equation. So characteristics equation means what? It is a Boolean equation that relates your input with your inputs and present state with your next state. So this you can say even as present state, and this is your next state. Okay, so this is your present state, or you can even say past state and this one as present state. But usually in all the textbook, this is referred as present state, this is referred as next state. So characteristics equation basically relates your input and present state with your next state. Okay, so let us try to do that. So if we make a K map, is directly also we could have written, but it's okay. So look at the places, it is 1. So at this 1 4 5, so 1 4 5 we have 1, and 6 7 we have don't care. So 6 7 we have don't care. So now let us do what? Groupings. So this will be one group of 4, and this will be one group of 2. So you can see what? Qn plus 1 is equal to, because I am writing for Qn plus 1 only, Qn plus 1 is equal to, in this 4 cell, S is common. So S plus, in this 2 cell, what is common? RQN complement. So this is the next state equation. Next state equation of SR flip-flop. Okay, so if you know the input and the present state, you can get the next state using this next state equation. Is this clear, Shriyari? Shriyari, is this clear to you?
Clear, sir, clear.
Okay. Now let us discuss about excitation table. So what is this excitation table? So excitation table, basically, in excitation table, what we do, we see the present state and next state to make a comment about our inputs. So what I said, in excitation table, basically what we do, we look at present state and next state to make a comment about your inputs. So how do we do that? We take help of your characteristics table. So look very carefully. Okay, so combination of present state and next state, it can be like this.
So look in this table. Whenever Qn is 0, 0, okay, Qn is 0, 0. What is the combination of 0? So 0, 0 is present over here. Any other place we have 0, 0. So one more place is 0, 0 is present over here. So what is the condition of S and R? So S, in this case, S is 0, R is 0. In this case, S is equal to 0, R is equal to 1. So we are going to write 1 don't care, because R can be anything. It can be either 0 or it can be 1. So that is why I am writing 1 don't care. Similarly, C, in the characteristics table, where we have value of Qn as, yes, tell me.
So it's 0 don't care.
Oh yes, 0 don't care, sorry. I told you guys I am struggling a little bit with this, means cough and cold, okay, today. So look, next, where we have Qn 0 and Qn plus 1, 1. So we have 0, 1 at this place, okay. Any other place that we have 0, 1? So no other place we have 0, 1. Now don't take this case, okay. This is don't care. We don't know exactly what will be the condition. So for this 0, 1, you can see state is 1, 0. So write it as 1, 0. Now see 1, 0. For 1, 0, when Qn is 1, Qn plus 1 is 0. So only at this place we have. Any other place we don't have. So for this we have 0, 1. Now look for 1, 1. So 1, 1 we have at this place and also at this place. So for 1, 1, here it is 0, 0. Here it is 1, 0. Okay. So this is 0, 0. This is 1, 0. So we are going to write don't care 0. Okay. Don't care 0. Now you might be wondering how to remember this excitation table. So you need to always remember this two, next state equation and excitation table. So there is one small trick to remember excitation table. How? So I will share that trick with you. Or else let me do one thing. Let me first discuss with you all the flip-flops, and then I am going to discuss the shortcut for remembering all the excitation table. Okay, so first let me discuss all other flip-flops also, and then we are going to discuss the shortcut trick for remembering excitation table. So this two thing needs to be remembered, next state equation and excitation table, because every time for getting this you cannot do, because when we design counter in our next class we will do that. So at that time we will be requiring excitation table and even next state equation. So you cannot go and write all these things. Okay. So next is what? Next we have D flip-flop, also known as delay flip-flop. So the delay flip-flop, basically it is used to get some delay. Okay, delay in the circuit. So that is why the name D flip-flop. So D flip-flop, it can be constructed using a SR flip-flop and one inverter. Okay, one inverter and one SR flip-flop can be used to construct one D flip-flop. So this is the structure. So this you can see this part. So this is your SR flip-flop using NAND gate. This is your SR flip-flop using NOR gate. Okay. So we have what? We have your D flip-flop. And how do we construct that? Simply connect your S to D, okay, S to D and R to D complement. So you can see I have made one D over here and D complement. So the simple thing is that you are operating the SR flip-flop, either, in which case either you will apply, means if you apply D as 1, if you apply D equal to 1, so what will happen? Set will be 1, reset will be 0. Or if you apply D as 0, set will be 0, reset will be 1. So you are always doing what? You are applying 0, 1 or 1, 0. So you are basically running the flip-flop, SR flip-flop in your reset or set state. Okay, reset or set state. S is connected to D and R is connected to D complement. So this thing needs to be noted. Now look, truth table for this one. So clock can be 0 or this can be 1 or 1. So if clock is 0, what will happen? Clock 0 means what? It doesn't matter, whatever is D, set will be, means if it is anything, so what will happen? If this clock is 0, D is 1, it doesn't matter, still set will be 0, reset will be 0. Okay, so this I am putting don't care, so this will be hold state, because just now we have seen when we put clock 0 in your SR flip flop, so what will happen? It will go in hold state. Now assume if clock is 1 and D is 0, T is 0. So if D is 0, over here set is 0, reset is 0, and over here also set is 0, reset is, sorry, means what I am doing. Set is 0, reset is 1, set is 0, reset is 1. So whenever set 0, reset 1 we have, what do we get in output? Output will be normal 1 0. Sorry, it will be 0 1. Okay, 0 1. Now assume if D is 1, so what will happen? If D is 1, so this will be 1, this point will be 0, even this will be 1, this will be 0. So set input in both the cases is 1 and reset is 0. So set input 1 means what? Normal output will be 1 and complemented will be 0. So look very carefully, why is this called as delay also? Whatever input you apply, same output you are getting in both the cases. So that is why this is also known as your what? It is known as your delay gate, due to the fact that whatever input we give, same output we get. Srihari, did we understand this concept?
Yes, sir. Clear.
Any doubts in this?
No.
Okay, fine. So now let us do what? Let us make the characteristics table. So characteristics table. Okay, so I have written it over here. So characteristics table, I have already told you, it relates your input and present state with your next state. So dn is equal to 0 means what? That basically your output will be 0, because over here you can see it is not depending on any of the present state, except when clock is 0, at that time your present state is mattering in the next state, but in all the other places whatever is your D, same is your next state. So here you can see dn means the input that I have applied in the present state, and qn plus 1 means the output, normal output that I am getting in the next state. Okay, so don't get confused what is this dn. Okay, don't get confused. So look, it is 0 still over here, this will be 1, this will be 1. Okay, so now if I want to write qn plus 1, so this will be what? Qn plus 1 is simply dn. So this is the next state equation of D flip-flop. Now if I want to write the excitation table, so excitation table I have already told that excitation table is the combination of present state, so this is your present state, and next state to get the input. So this can be 0 0 0 1 1 0 1 1. Okay, so now if it is 0 0, so you can see what? Look over here, if qn is 0, qn plus 1 is 0, dn is 0. If qn is 0, okay, and dn is 1, what is, sorry, qn is 0, qn plus 1 is 1, so dn is 1. Okay, if qn plus 1, sorry, qn is 1, so qn is 1, qn plus 1 is 0, dn is 0. If both of them are 1 1, this is the case, so dn is 1. So this is the excitation table. or simply you could have taken help from here also. Whatever is Qn plus 1, same will be Dn. So you just copy this column into Dn and you will get the excitation table for D flip-flop. Any doubts up to this point? Any doubt?
No, no,
Okay, chalo. The next concept is what? Very important. It is your JK flip-flop. So JK flip-flop, why do we, first of all, let us note, why do we use JK flip-flop? Why don't we, means what is the necessity of JK flip-flop? Can you tell? What is the necessity of JK flip-flop?
To use the invalid state actually.
Yes, very good. So we need to remove the invalid state. So when was this invalid state coming? Invalid state was coming when basically both the inputs are either 1 1, okay, means both the inputs when it is 1 1 to either of the flip flop, or you can say in latch when both the inputs are either 1 1 or 0 0. In case of NOR flip flop, when both the NOR latch, when both the inputs are 1 1, we had invalid. In case of NAND latch, when both the inputs are 0 0, we have invalid. But in your flip flop, when irrespective of NAND or NOR, whenever both the inputs are 1 1, we have what? We have invalid state. So in JK flip flop, basically we are going to counter this only. Other than this invalid state, JK flip flop is same as your SR flip flop. So I guess I have directly made the table over here. So it's okay. See, because over here we have taken this feedback from your present state to your input, and normal means complemented also we have taken, and normal also. Just remember this. In J, if I want to convert SR flip flop to JK, so then your complemented present state should be connected to S. Okay, you can see over here I have connected to S, and your normal should be connected to R in SR flip flop circuit. Okay, and remember this, JK flip flop is just like SR flip flop, where J corresponds to S and R corresponds to, sorry, K corresponds to R. See, I am very sorry that I cannot go in very depth that why all this thing is happening, because it will take a lot of time and we don't have that much time. But still, if you remember this much, everything will be very easy. So when clock is 0, what will happen? So anything you want to ask, Srihari?
That is that an AND gate? I don't actually remember it. Like that input area, S and R area.
What? I am not able to hear you.
In the diagram of this flip-flop,
Yes.
the S and R area, is that actually NOR gate or simply this AND gate?
This AND gate. See, SR flip flop. This is SR flip flop. If I don't have this, this is normal SR flip flop. Okay, normal SR flip flop. So for converting it to your JK flip flop, I need to have this feedback. Okay, so basically what? Basically your JK flip flop is what? It is your feedback. We have a feedback. You will see. You will see. Okay, why we have this flip flop? What is the use of this flip flop? We are going to see that. Tell me, if you have any other doubt, you can ask.
Nothing,
okay?
sir.
Okay. So okay. So yes, this is okay. Okay. So now see, whenever clock is 0 0, means clock is 0. So let me assume this is S and this is J. So you can see this will be hold state. When clock is 1, but both the J and K input is 0. See, if you put J 0, K 0, as this is AND gate, so obviously output will be 0 if one of the input is 0. So if we apply 0 0 to your NOR latch, obviously it will be hold state. This will be also hold. Okay. Even in this case also, this will be hold, means over here, I shouldn't be writing it like this because we already have your present state defined. So if it is Qn, so next state will be also 0 1, because if your present state is 0, so next state will be also holded. Same for here also, this will be also hold. So 1 0, this will be holded because J and K both of them are 0. Now look very carefully. If S is Z, means J is 0, K is 1. So J 0, K 1. So if this is 0, it doesn't matter. Whatever is another inputs over here, this will be immediately 0. If this is 0 and this is 1, clock is 1. Okay, even clock is 1. Look at this place. Look what is your Qn. Qn is 0. So even this is 0. Okay, even this is 0. So again I am getting hold state or what? So have I done some mistake or what? In this case, Qn is 0, J 0, it's okay, and K is 1. Okay, so S is 0, J is 1, sorry, J is 0, K is 1. Let me do it once again. You know, clock is 1 every time, and J is, where is our case? This case. Okay, so this 3 are hold cases only. Now this case I am talking about when J is 0, K is 1. So J 0, K 1. So if this is 0, this will be 0. And if this is 1, clock is 1. What about this state? So Qn over here is 0. So this is also 0. So 0 0. So again I am getting this as what? Hold state. So hold state, basically if I hold this value, so this will be 0, this will be 1. Okay, fine. So this is correct. Look, see, at the moment you might not be understanding, but let us first fill the tables. Okay, so look very carefully. Now next is what? Look at the table. Next is this case. Clock is still 1, J is 0, K is 1. So J is 0, K is 1, but next state has changed. Next state is now 1. So if this is 1, so obviously we will be getting what? We will be getting 1 over here, and means this is 1 1 1 and this is 0. Okay, so this is 1, this is 0. So the moment you get this as 1, this will be 0 and this will be 1. Okay, this will be 0, this will be 1. So this is what? So this is 0. Still you can see this is 0, this is 1. Okay, tell me if this is clear or not. Is this clear? See,
Yes, sir.
basically what I am telling, see, J corresponds to S, K corresponds to R. So you haven't changed J in both the cases. J corresponds to S. So in both the cases, set input is 0 in these two cases. So set input is 0 means what? Reset input should be high. You can see K input is 1 in both the cases. So we are getting the condition of reset only. This is reset. Complemented output is 1 and normal output is 0. So this is reset. Now look for these two cases. For these two cases. So first let us consider this. J1 and K0. So J1 K0 in this case, and your present state is 0. So if this is 0, this should be 1. So now let us see what we get. If this is 1, this is 1, so obviously this is going to be 1, and over here this is 0. Okay, so if this is 1, this will become 0 in the next state, and if this is 0, this will become 1. Okay, this will become 1. So your normal output is 1 and this is 0. Similarly, if you put once again, you will get 1 0. So these two are set case. Set. Now look at these two last cases. Previously we were getting what? We were getting invalid, but this time look what we get. Both J and K are 1 in the first case, along with Q and 0. So if this is 0, so this will be 1. Okay, this is your present state. So now let us calculate the next state. So if this is 0, this will be feedback over here. So this will be what? This will become 0. And all the three of them are 1 over here. So if this is 1, this is 0. The next state will be what? This will be 0. And this is going to be 1. So look very carefully. My present state was 0. But look at the next state. Next state is 1 and complemented is 0. So basically I am toggling the present state to next state. Toggle means what? Toggle means basically complement of one another, or it has changed state. So your present state was 0, the next state is coming out to be 1 0. This is not your what? This is not your set. This is your toggle state. This is toggle. See, you can see condition is same as set, but this is not set. This is toggle. This is toggle because we are getting this for a different set of input. Here both the inputs are 1 1. So when we get toggle, when both the inputs are 1 1. Now again J and K is 1, but this time your present state is also 1. So if present state is 1, so complemented present state will be 0. Let us calculate the next state. So this one will be feedback over here. So output of this will be 1, and this is 0, means output of this is 0. So if this is 1, next state will be 1 over here. Sorry, next state will be 0 over here, and this will be 1. So you can see this is 0, this is 1. Again your present state has toggled in the next state. If your present state was 1, next state is becoming 0. Tell me if this is clear or not. Theory, is this clear? Okay, fine. So you had some doubt in the starting. So now is it clear?
Yes, once in that diagram, I had while drawing the diagram, we have to use all the, whether it's NOR, everything will be NOR. It's NAND, everything will be NAND. That kind of.
Okay, you can do. We know actually how to implement AND using NOR. Okay, but that will do what? That will increase the complexity over here. I don't want to increase the complexity. Okay, I don't want to increase the. So that is why I have taken a simple AND. You know basically how to make AND gate using NOR. So that is something like this. Okay, so whatever you do, then you will be getting what? You will be getting, means this is AB, so this will be A complement, B complement, so this will be AB. So you know how to make AND gate using your what? Using your this thing, NOR gate. So I don't want to basically increase the complexity. That is why I have constructed it like this. Now let us do the same thing for your NAND gate. Okay, Nand Latch. So now I am not doing this. Okay, same thing you will get whatever we have got over here. Same thing. So I want you to do this as homework. Okay, so in Friday's session we are going to have this one. So today I will end over here. Okay, so it's okay. So today we couldn't finish this. In the next class, what we will do, in the next class we are going to finish counter. Most probably counter will be finished, and in next to next class register will also be finished, because this is one big chapter we have, and very good questions, numerical questions and objective questions will be asked from this topic also. Okay, so that is why this topic, it will take a little bit of time, and then we have remaining this topic, what ADC and DAC, that will be finished in just one class, and with that we will be finishing digital. Okay,
Okay, okay.
okay, so today we are stopping over here. Okay, so same thing if you do. So I want you to write the characteristics and excitation table, or simply you just take this screenshot of this and fill the truth table of this JK flip flop using your NAND latch. Okay.